whatever appears on the right hand side is now going to be interpreted as normal. Okay, so the operator O is expanded in a series of normal ordered expressions according to this equation. Is this clear? For instance, let's see that work at the quadratic order. Suppose we had x of sigma 1 times x of sigma 2. This equation will tell us that it's equal to normal order x of sigma 1 plus x of sigma 2. Plus, now these derivatives get to act. Since there are only two operators on the right hand side, we can expand this exponential to linear ordering exponential. We get plus alpha prime times 2 log of z1 minus z2 squared times nothing sigma 1 minus sigma. And this is the same thing as what we defined before, because this quantity is minus of this 2. Is this clear? Okay, let's put this normal order here. Now the great thing about an operator expression like this, and an equation like this, once you have such an equation, it's very easy to invert. Once you have such an equation, it's very easy to invert. So suppose you want to know what is normal order to O. Well, what is that? Well, it's simply exponential with minus alpha times 2. Acting on O. Okay, so this gives us an inverse relation, telling us how we. This is a direct definition now of normal. Now recursive. I'm sorry, I got these signs wrong. If I wanted the operator itself, I wanted the 2 sorry, I got the sign wrong. This minus this plus. You see that, right? The operator is normal order plus 2 point function. So the operator is normal order plus 2 point function. Normal order is operator minus 2. And the 2 point function has minus alpha. Is this clear? Have I confused you with the signs? Okay? Sorry. Okay. Which side? This. Yes. It should be negative, right? Right. Exactly. Okay. Now, the last formula I want to I want to tell you about is a formula that allows you to expand the product to normal ordered operators in terms of normal ordered operators. Okay? So first let's say it intuitively and then there's an equation. You see, inside normal ordering, you've subtracted away all contractions between operators that you have. But if you were to normal order the whole thing, you would have to subtract away also cross contractions. Okay? So intuitively what's going on? Suppose you've got the product of 2 normal ordered expressions. Then it's equal to the whole thing normal ordered plus whatever you would have got. It's equal to the whole thing normal ordered plus whatever you would have got in that normal ordering procedure that involves cross contractions. Okay? Let's put that intuitive statement into an equation. Okay, so suppose that a normal order O times normal order A normal order O times normal order F, then then what I need to do is to and I want to write it as some object times normal order OF. Okay? This thing has additional singularities coming from contractions of, so we get a minus alpha prime. Actually, I have no 2 now, as you see. Minus alpha prime log of z1 minus z2 del by del x of z1 del by del x of z2 such that z1 acts only on O and z2 acts only on F. Sorry? No. Then, okay. Either we don't have a 2. The first acts and the second acts and the second. Yeah. Or we have a one half of first acting on first acting on second, and all both the process will become. Right. And then if you have a 1/2. Then you should allow 2 kinds of terms. First acting on first, second acting on. No, the alpha prime by 2 was in the 2-point function. Yes. Okay, go on. Okay, so that's fine. Then now there will be 2 kinds of terms in which the first one acts on O, second one acts on F. That is one kind of a term. The second is the first one acting on F and the second. Yeah. So let's say that this guy acts. Z1 acts only on O, Z2 acts only on F. Then the 2 won't be there because we are double that. Oh, maybe you're right. Let me just check this out in a particular case. Suppose we want x of sigma 1 times x of sigma 2. Okay, this is normal order by itself. This is normal order. I want to expand it. We know the right answer is normal order of x of sigma 1, x of sigma 2 minus alpha prime by 2 log of z minus sigma 1 and sigma 2 squared. This is the correct answer. Okay. Now, square 1. So now let's use the definition. Suppose we use x of minus alpha prime by 2 log of sigma 1 minus sigma 2 mod square times del by del x of sigma 1 by this one acts only on this guy times del by del x of sigma 2, but this guy acts only on this guy. Okay, acting on x of sigma 1, x of sigma 2. Okay, so we get the right minus alpha prime by 2 logs. Right, there will be ways of writing it with different factors depending on what you. If you say that this is allowed to act on both, then we would require an additional half. Then we would require an alpha prime by 4. Right? So fixing one convention, our convention being that the first derivative acts only on the first operator, second derivative acts only on the second operator, then we just have this. Okay? Great. So this is the formula that allows you to take a product of normal order operators and expand it in a series of normal order operators. Okay. So in the last 10-15 minutes of this class, so we finished this form. Yeah. So we finished our formal discussion of normal order. Okay. Whenever I write down a product of operators from now on in this area, I would always mean normal ordered products. Okay, if it's confusing, please ask me. But in general, I will always mean normal ordered product. I'm often not going to use the normal ordering symbol just because it's so cumbersome. Okay, so now we go back to the question of what is the stress tensor here. one that consistency will show is correct, is that the stress tensor normal order then x. At least this is a sensible expression. At least it's a sensible expression. And, you know, okay. This is a postulate for stress tensors. If we're off by a constant, that can sometimes happen when you define operators wrong. We'd see it when you do, for instance, expansions. If you define things a little differently, you might be off with it. Okay, this is our definition of the stress tensor. Fine. Now that we've got a stress tensor, let's try to compute the TTU. Okay, so what we want is T of Z times T of W. So that's the same thing as minus 1 by alpha prime T. So let's cancel the minuses. T del x of Z del x of W, del x of Z times 1 by alpha prime del x of W del x of W. Remember, these guys were normal ordered within themselves. Okay, let me write that. These guys were normal ordered within themselves. Now, what we are going to try to do is to re-expand this product of normal ordered operators in a series of operators, each of which is completely normal ordered. Why are we going to try to do that? You see, we have already argued that inside normal ordering, there can be no singularities. Okay? So anything that appears inside normal ordering will be, you can honestly Taylor expand. All the singularities will appear in the process of normal ordering. Okay? So in order to complete the singular terms in the OPE, all we have to do is to normal order the sole expression. So how do we do that? Well, the rule is choose all possible pairs and contract. So first let's look at contractions that we get, by total contractions. This with this, or the other way around. There are two such terms. Each of us give us what? See, x with x was minus alpha prime by 2 log. Now we take one derivative with respect to w and one derivative with respect to z. The first derivative, if it was taken with respect to z, gives us no minus sign. The second derivative taken with respect to w also gives us no minus sign. Because 1 over x differentiated gives us minus sign, but we're differentiating 1 over minus x with respect to minus x. Therefore, we find that del x, so let's note down this thing as a useful thing to remember. Del x of z, del x of w is equal to minus alpha prime by 2, 1 over z minus w. This part. Okay, so now let's do it. Let's do the terms in which we've got all contractions. What do we get? We get two of these factors. So we get alpha prime by 2 with a minus sign, the whole thing squared. We had a 1 over alpha prime squared. And we have two of them, so we've got a factor of 2. And we get a 1 over z minus w. This simplifies to half of z minus w. So the term in which everything is contracted away is half of z minus w the whole. Is this clear? Clear? Okay? What about the next term? What about the term in which just two of the x's are contracted? Okay? What about the term in which just two of the x's are contracted? Well, in that term, we have a factor of 4 because we have two ways of choosing which to contract here, two ways of choosing which to contract here. Okay, so firstly we have a factor of 4. Then we get we have 1 over alpha prime squared from the overall factor, we have minus alpha prime by 2, and then del x of z, del x of w, and z minus w. Let's simplify this. This is equal to minus 2 by alpha prime, del x of z, del x of w, is z minus w. We'll return to this term, but before doing that, what about terms? What about terms in which we have? What about terms in which we have everything contracted away? I mean, sorry, nothing contracted away. Well, so the last term is normal order of del x of z squared del x of w squared normal order of this thing with a 1 over alpha squared. This term can have no singularities because this correlation, this normal order operator product is genuinely analytic in insertion points of the operators. Okay, so this thing is completely nonsense. Good. So we've already identified all terms that can give us singularities. What have we got? So let's rewrite the singular term. We've got half of z minus w the whole case. So 4 plus 2 into minus 1 by alpha prime del x of w del x of z by z minus w squared. This thing is normal. Now you might think that this is it, and this thing looks awfully like twice the stress tensor. So you might be wondering, what about the other term? What about the term that has 1 over z minus w? And the point is this, that while these expressions are completely analytic, of course they do have a Taylor series expansion. So remember that one of these was a w, the other one was a z. Okay? So when we expand it to write it in the form where everything is a w, we need to take this del x of z and rewrite it as del squared x of z, del x of w plus z minus w del squared x of z. Because everything is analytic and honestly perform a Taylor series expansion inside normal. Okay? So we concluded that the singular part of PE is half z minus w to the 4 plus 2 times t of w z minus w squared, and then plus, you see, this, the fact, we've got a second derivative acting on one of the x's in this term, but we can symmetrize that. So we can write this as plus, and remove the factor of 2. So del x of w del x of w over z minus w with minus 1 there, which is half of z minus w over 4 plus 2t of w z minus w squared plus del t w. Okay? So we cover the standard form for the operator product expansion of the stress tensor, except this time with the specific value of the central charge, C is equal to 1. Is this clear? Okay, let's move on. Let's perform a few more manipulations with this free scalar conformity. It's so much fun. Basically, it was so easy. It's free theory. You can do any calculation you want. The next thing I'm going to try to do is try to the end of that. Is try to discover some primary operators in that theory. Okay. So claim that del x is a primary operator. Okay, so I claim that del x is a primary operator. Why is that? Okay, in order to check that an operator is primary, all we need to do is compute the operator product expansion of the stress extensive of the operator. Let's do that. We have minus 1 by alpha prime del x times del x, let's say at z, times del x at w. Let's do the calculation. Well, we can contract once or not at all. Alright? So let's do the contraction once. Okay? The contraction once, we have a factor of 2 from which one of these two contracts. So we get minus 1 by alpha prime times 2 times minus alpha prime by, we had minus alpha prime by 2 times 1 over z minus w the whole thing square times del x at z. Plus the term where everything is non-logic, so plus 1. Okay? So that gives us del x at z over z minus w the whole thing square plus 1. Now once again we have to Taylor expand this. Because in the standard form we should have operators instead of only at w. Okay? So this can be written as du plus del of del x at w over z minus w plus regular. You see, this is the standard form of the operator product of T with O if O is primary, and here we've identified so del x is primary operator with h equals 1. Right, because h is the coefficient of this term here. Is this clear? Is this clear? Okay, let's do one more little calculation. Can you guys take a look at 1:5? Okay, we're missing so many classes that I want to move a little bit. This Friday also, by the way, I'll be going for a conference, so I won't be around. It's almost like we're doing one class a week, so we need to have this class. Okay. So now let's try to do one more such calculation. Okay, the calculation we're going to try to do is to demonstrate that e to the power kx is a primary. Let's do it. You see, what we want, once again, is minus 1 by alpha prime del x times e to the power kx. Now, e to the power kx, well, you can use a formula that actually simplifies matters in this case. Let's just do it by hand. Let's sum, and let's write its Taylor series expansion as I k to the power m by m factorial times x to the power m. Okay, so this is at z, and this is at w. And on the opening. Okay, so since there are only two operators in T, I can do either one contraction or two. Okay, let me first do the guy with the two contractions. I'll leave the guy with one contraction for you as well. Oh. Let me do the guy with two contractions. Guy with two contractions, let's say, suppose I have this guy hitting the guy with M. First guy has a choice of n fellows with which to contract, and then the second guy has a choice for n minus 1. Okay? So we get a minus 1 by alpha prime times m into m minus 1 times, let's put the sum here. Then we get ik squared times m, well, let's try this, m times m into n minus 1 by n factorial. And then two of these guys are removed. The next 5 minus 2. And then we have z minus w, the whole thing squared, with a minus alpha prime, right? No minus, plus alpha prime by 2 to the minus squared. It's two equations. Now, you see, we've got x to the power n minus 2, and this m into n minus 1 is make this an n minus 2 value. So if I just take an ik squared, ik the whole thing squared out here, I can resum the series. Okay? So let's just get the factors right. So we had alpha prime minus alpha prime by 4 times ik squared, so that makes it plus k squared. And then we get e to the power I k x. The whole thing by z minus w. Okay, I'm going to leave it as an exercise for you to show that the guys with one contraction will give us the remaining term, the derivative of exponential. So this is indeed the operator product expansion with stress tensor in the primary field, and we've identified that h, the weight, is equal to alpha prime by 4 k squared. Okay, so we identify the whole class, very many primary operators. Okay, the last thing, the last thing that I want to do in this theory is to talk a little bit about the Hilbert space interpretation and the state operator. Okay, so let's discuss the Hilbert space operation, the Hilbert space interpretation of the state. Now, if you go back to your notes and review how we introduced oscillators in the quantization of these x's, you'll find that we introduced oscillators which had funny combination relations. Alpha n times alpha minus n was equal to n rather than 1. Okay? You take that the expansion we had performed in the W, the cylinder plane, and convert it into an expansion in the Z plane. In the cylinder plane, we had something rather simple. We had just a usual standard Fourier series expansion with square root alpha prime by 2 outside. In performing the map from W to the Z plane, we pick up a factor of minus I and a factor of 1 over Z. So the expansion that we've done in class previously, when mapped to the Z plane, simply becomes the following expansion. When we get factors correct, becomes the expansion del x of Z is equal to minus I square root of alpha prime by 2. Sum m is equal to minus infinity to infinity alpha m divided by Z. Okay? Z, the plus 1 here is simply the fact that primary operators transform with the relational factor of Z to the power weight. Okay, and the minus I was the same reason. Right, you remember del W where del Z was minus I times Z or I times Z. Okay, so now this anyway is our definition of the mode operators alpha m. So del x is an analytic operator, and we've extracted in the most general Laurent expansion. So it's a completely general thing to do, but we've chosen factors carefully so that it agrees with these alpha m's are the creation and annihilation operators that we talked about before. Just to remind you again, alpha m's with m's positive are annihilation operators, alpha m to the n is negative are creation operators, and the commutation relation is alpha m with alpha n is plus m times delta n plus n. Okay, that's how we worked it out last time. Let's actually check directly that these commutation relations come out. How do we do that? We use the kind of calculations we used to derive the Minwalla solution. Remember, we want what we want. So, suppose we want alpha m. Okay, that is equal to 1 by 2 pi I times 2 by alpha prime times I times z to the power m del x. Right? Alpha n is the same thing. Let's call it that. Okay? Now, if I want to compute the commutator alpha n commutator alpha n, what is this thing? Well, in the I'll have two of these. Where in the first expression I have m first, so inside. So this is z and w. And in the next expression I have n first and so inside. So this is w and z. So I'll usually first do the z integral to the point of w, do the z integral. Sorry, I said it the other way around, right? Sorry. So in the first expression I had, let me say it again. The first expression is alpha m alpha n. So alpha n is the operator that acts first, and so w is inside. And the next expression is z. Okay, so we do this. We choose some point in w and do the z integral. So what we get is, so we get the I. Let's take each of these i's and square them. So we get minus 1 times 2 by alpha prime. Now all that remains is the 2 pi i's. So integral dw by 2 pi I times the residue in z of the pole as z to the power m del x, w to the power m del x. Okay, so let's compute this OPE. So what we get z to the power m, w to the power n, and then 1 over, now we have del x, which is minus alpha prime by 2. So that cancels this alpha prime by 2. So we get, what? Yeah. So we have dw by 2 pi I, and then z to the m, w to the n over z minus w the whole thing square. That's what we had, but we want the residue of the pole in it. Since we got the square down here, we want to expand this once. So really what we have is dw by 2 pi I, and then m times w to the power n plus m minus 1. Which is equal to m times delta function of n plus m. So what we concluded? We concluded that alpha m alpha n is equal to delta of m plus n 0 at l, which was a commutational relations, if you remember, we used when we were doing our quantization. It's always, by the way, a safe thing once you write down your relations just in z coordinates to directly check the commutational relations. You might have made a factor mistake. This will very easily tell you. It's much easier than tracing through all the conventions that go from translating from one picture to the other. Okay, great. So we've got this nice expression. We've got this nice formula now. We've got a more expansion of x in terms of these oscillators that are based on standard computation relations. Okay. Now, the next thing I want to try to understand is the state operator map. The next thing I want to try to understand is the state operator map in this theory. You remember we have this nice general theory which told us that for every operator insertion there's a corresponding state and vice versa. What I want to do is to discover what the operator due to any state is, or what the state due to any operator is, completely in this theory. Okay, so let's remind ourselves what the spectrum of states was in the theory. Okay, so what was the spectrum of states in the theory? Firstly, you had some wave functions for 0 volts. You had a wave function for 0 volts. And in addition to that, you have all the various oscillators. The most general state was alpha minus 1 to the power m1, alpha minus 2 to the power m2, alpha minus n to the power mn acting on vacuum, all the way acting on vacuum, times a wave function for times e to the power ikx0 times integral. And so this is the basic. Then of course we take linear combinations. X0 is the 0 root. Remember, this was the quantization of the system. That we have arbitrary wave functions from 0 volt times oscillator excitations. So we immediately says there should be a dual operator. Let's try to discover the dual operators. Okay? We're going to try to do this discovery in several ways. Today we only have time for one of these ways. Okay? This first way is by experimentation. Okay. So the first question I'm going to ask is, what is the dual of the identity operator? We know it should be the vacuum state. We know it should be the vacuum state. But let's try to understand this in a way that is sort of nice. Okay. And that will generalize to other things. Okay. If the dual of the identity operator was the vacuum state, okay, then what must in particular be true? In particular, it should be annihilated by every annihilation oscillator operator. Right? So it must. So suppose we take identity. The question I'm going to ask is, what is alpha n for all n positive? Alright. If I find that 0, well, that identifies it as a vacuum state, apart from possible e to the power ikx contributions. So let's check. What is alpha n on identity? Well, apart from irrelevant constants, that is simply z to the power m del x acting on identity, but that's nothing. Okay, z to the power m del x. But we know that by the equation of motion, del x is an analytic operator. Z to the power m is analytic as long as m is greater than 0. Therefore, this quantity is completely analytic. Okay, this quantity is being evaluated on this contour, but since it's analytic everywhere here, just consider. Okay, great. identity operator is the vacuum. But we'll come back to the zero mode portion. Up to zero mode subtleties, check that the identity operator is the vacuum. What about this nice primary operator that we have, del x? In fact, what about the operator del k of x? K derivative of that. K analytic derivative of x. And what about that? Well, let's try the same trick. Let's try to check what we get when we take z to the power m del x. So, this operator, whatever it is, let's calculate alpha m acting on del k of x. So, all we have to do is to take this operator, surround it, and then put del k of x at 0 and see what we get. Yeah, omitting constants, because all I want to see is whether it's 0 or you know, what's we can work it out with constants. Carefully. Okay, but what do we get here? So we get here z to the power m 1 over z to the power k plus 1. And times constants. That's k plus 2, k plus 2. Sorry, k plus. No. K plus 2, k plus 2. Right? Right. Okay? Now, this thing is non-zero only if m minus k is 0. Because now we're going to contour the integral and we become the residue of the pole. This is a pole only if n minus k is 0. Okay? So there is some constant times delta of m minus mk.
Sorry, why was that 1 by k?
Because x with x is a log, and then you differentiate k. Okay? So what did we find? We found that every annihilation operator except the kth one annihilates the state, and the action of the kth state gives you a state proportional to identity. So this is the k. Therefore, this state must be proportional to alpha minus k. It's the only state that has this property. That is annihilated by all annihilation operators except the kth state, kth one, and the action of the kth annihilation operator gives you identity, the vacuum. Okay? Proceeding in this manner, okay, we really must stop now, about 1 hour over time. So, proceeding in this manner, I'm going to ask you to check the following. I'm going to ask you to check that del k x to the power mk product over all k is dual to the operator alpha minus k to the power k product over all k. Okay? The next exercise I'm going to suggest to you is see if you can argue that, so we found the dual of the operator state correspondence for all states except for the zero mode part. What about the zero mode part? If you want to add the zero mode part, what you should be doing is put the operator in pi x. That gives you the equal. Remember, e to the power I k was nice primary operator. 1. Okay? I'm saying that this is the full state operator in this theory. Okay? I'd like you guys to check this in any way, in as much detail as you can before we meet next class. Okay? That completes at least one way of thinking of the state operator in this theory. Now there are several other things one can do with the free boson. And something that people do a lot, though I never find it terribly useful, is to write down the Virasoro generators in terms of the free boson oscillators. and then do a lot of manipulations using oscillator algebra. Somehow I don't find that very useful. But it's a game people play very much, and perhaps it's sometimes useful. Okay? Other thing that's more useful, in my opinion, for you to try is to try some direct path and technical computations in this area. Okay, so I'm going to suggest one more exercise for you, again that we'll discuss at the beginning of the next class. Just directly by path integral analysis, compute the path integral with del k of x inserted at the origin. Okay, and show that it is the wave function for the kth oscillation. Okay, once you've done all these exercises, you know enough about the free boson theory for my purposes. So this concludes our discussion. This essentially concludes, apart from discussing the exercises that we talked about, this essentially concludes our discussion of the free boson conformal theory. In the next class, I will describe some slightly more complicated conformal theories. Okay, we'll talk about some slightly more complicated conformal theories. And in the next class will be on Wednesday. And the class after that, which I hope will really be on next Friday, we'll then go back to taking all that we've learned about conformal theory and applying it to our study of string theory. So our long interlude into the study of conformal theory will be finished. We've almost finished, but at the end of the next class we will cover every bit of material in chapter 2 of Polchinski. So if you people feel like reading Polchinski's chapter 2 now, everything except the part about the more complicated conformal theories should be completely intelligible. In the next class, I'll also suggest a set of exercises, problems at the back of Polchinski.